Welcome to the online causal inference seminar. Today we have Ilya Shpitser from Johns Hopkins talk about identification estimation in graphical models of missing data. We're very excited about the talk. So one of his collaborators, Rohit, is also here in Q&A today and will try to answer all your questions. Ilya will also stop from time to time to take questions from the audience. After the talk, we will have a discussion by Tian, and then if we have some more time, we will take additional questions from the audience. All right, that's it from my side for now. Thank you all for coming. I'm now switching over to Guillaume.
Thank you, Dominic. So as Dominic said, we have Rohit this week who will be manning the Q&A section. So please submit questions and he will do his best to answer them directly if he can. And we'll try to select some questions to ask to Ilya. So the way this is going to work, as usual, is if your question is selected, I will ask you if you're willing to voice it yourself. And if you are, I will ask you please to raise your hand. You have a button on the menu bar to do that. As usual, please do not press that button unless I've asked you to do so. That just makes it more complicated to handle the Q&A. So thank you very much. And now let me turn the mic to Ilya. Ilya, whenever you're ready.
Great. Thank you very much. Thank you, organizers, for inviting me. It's an honor to speak here. And also thank you for running such a wonderful and smooth seminar. It's not easy to do the logistics, of course. And I wanted to take a minute or two just to make two quick announcements before my talk. So as some of you may know, me and my friends have been trying to start a society for causal inference. As folks on this call probably know, causal inference is becoming a very popular area of study, and there are many approaches now from all sorts of different areas of data science, like classical statistics, econometrics, philosophy, machine learning, computer science. But despite all this, there's a bit of a unique character to causal inference, and of course, this COVID pandemic is just showing how needed causal inference are. It's becoming a bit of a masterclass of sort of making decisions and analysis with censored data and all sorts of selection bias and dependent data and problems like that. And so we, by which I mean Jennifer Hill, Luke Keel, Dylan Small, Stephen Cole, and myself, are trying to kind of bootstrap a professional society for causal inference researchers. And we also have kind of a larger group of people, which is the development committee, which are the past organizers of the Atlantic Causal Inference Conference. So we already have kind of a conference for causal people. The goal is to, once we're up and running, we'll sort of open up the governance, and we would like to solicit involvement from all corners of our community and hold elections and so on. And the vision is to kind of, for this society to be a link between academia, government, and industry, and to sort of serve as a career resource, and to have all voices from our diverse community represented. I think that's important. And so we have a website now. We are running a logo contest, by the way, if you have clever ideas on what the society's logo should be. So please check it out. So that's SCI. And another quick announcement is I'm pleased to announce the release of this software called Ananke, written by wonderful and talented students in my lab. Ananke, of course, is the Greek goddess of necessity. This software package is written in Python, which is a bit of a kind of a machine learning standard these days, and it is able to sort of programmatically do a lot of the causal inference stuff that people do, including identification, if you wanted to see how things are identified in complex models, and further, given an identified causal parameter, how you might go about estimating this parameter, including sort of semi-parametric methods, which have become very popular recently. And so here is some documentation links and GitLab. You can just download it and play with it. And here's a quick example. You could specify all sorts of complex kind of longitudinal hidden variable models. And it will suggest various estimation strategies, including semi-parametric estimation. And we are, of course, aiming to extend it and add a bunch of functionality, including model selection and including some of the missing data stuff I'm going to talk about today. Okay, so with that, let me turn to my talk. This is a talk on missing data and graphical models with a bunch of collaborators. Eric Chetkin, and Jamie Robbins, many of you may already know. It's also joint work with Dan Malinsky, who is a postdoc in my lab, who is going to be joining Columbia Biostats this summer. And of course, my wonderful and talented students, Razia Nabi and Rohit Bhattacharya. Rohit's here to answer questions. And both of them are going to graduate soon and going to be looking for jobs. And I just wanted to say that this is just, this talk is just a part of the amazing work they do. They also work on all sorts of other things like semi-parametric inference and algorithmic fairness and model selection and network data. So please check out their work. They're amazing. Okay, so missing data. Anyone who does applied work knows that missing data is a serious problem. It arises in all sorts of ways.
Quick question, Ilya. So I think your screen froze. We currently can't see your talk slides. Can you?
Okay. Very sorry.
So you were still at your announcements. Can you perhaps stop screen sharing and start screen sharing again?
Okay, sure. Sorry about that.
All right. Yeah, now we can see it.
So you didn't see the pictures of my collaborators. Here they are.
Yes.
Can you see them now?
Yes, you can.
I'm very sorry about that. Okay. Everything I said is still true. Okay. Okay. Right. So missing data is a fact of life. It arises in all sorts of ways. In applied analyses, we have dropout. We have missingness because of the way survey sampling works. We have data collection issues. We have coarsened values for privacy reasons. We have censoring by death. If we're doing prediction problems in machine learning, we often have scarce outcome labels and all sorts of things like that. And so there are lots of approaches people have taken to missing data. And the way I chose to classify them in this talk is you model missing values or you model missingness status. So if you model missing values, you can sort of try to fit the full data likelihood, the observed data likelihood by EM or optimization methods. And then, of course, if you do that, it better be that you're identified or you can run into problems. Or we could try to impute, can use imputation. And a lot of imputation methods, it's not necessarily clear exactly what the model is and what it is that we're imputing. And I'll come back to this point a little later. And so the other thing you can do is you could model missingness status. And that you could use these inverse weighting propensity score methods, or you could also, I've used semi-parametric methods sort of in this camp as well, although you need additional modeling here. And so in this talk, I'm gonna think about missing data counterfactually, because I'm from Causal Inference, of course. So, so how do we do that? So we'll talk about missing variables with this little parentheses 1 superscript, and that means the variable xi if we could hypothetically observe it, which is not necessarily what actually happened. And so every such variable has an indicator Ri and a factual, so actually observed proxy variable. And these variables are related as follows. So xi is equal to the underlying variable if the indicator is 1, otherwise it's equal to question mark. And so this is sort of like a missing data version of the consistency property. And the analogy here is that the xi parentheses 1 is like a counterfactual, and then Ri is sort of like a treatment. Okay. So here's some, so that's how we're going to think about causal inference. And so here's some notation and terminology. So we'll use vector notation and we'll do -i to talk about all variables other than I. O is going to just be always observed variables, and we'll have a bunch of distributions that arise in missing data. We'll have the target law. Law is just all tiny way to say distribution, of course, which is the distribution over the counterfactuals and the observed variables. The nuisance law is sort of like the propensity score in missing data. It's the distribution of the missingness indicators or the observability indicators given the underlying variables. We have a coarsening model, which sort of encodes consistency. And we have the observed law, the observed data distribution, which is the proxies, the observed variables, and the indicators. And typically we want some function of the target law or the full law. And so by chain rule of probability, the target law can be expressed as this ratio where the numerator is observed data and the denominator is the propensity score. So essentially, if you want to identify some function of the target law, it's sort of like trying to identify the propensity score. It's the same thing. Okay, and so this is kind of a cartoon picture of missing data problems. You have some full data distribution, and in this distribution lives a parameter we want to make inferences on. And there is, if we had a full data problem, what would happen is we'd have independent, identically distributed realizations, and then we could just learn the parameter by usual methods there. Of course, in reality, what happens is there is a coarsening process that produces another distribution where the counterfactuals are kind of coarsened in some way, and then it is from that distribution that we get IID realizations, and then we have to do a missing data problem from those realizations to try to get at the underlying counterfactual parameter. Okay, so people have thought about missing data for a very long time. There are lots of missing data models. So I'm going to list a few on the slide. One of them, of course, is missing completely at random due to Don Rubin, where missingness indicators are basically independent of the unobserved data, or indeed of everything. There's a monotone missing at random model. Like one reference is fairly early that I found is by Robbins, Rudnitsky, and Zhao in '94, where you have this independent statement on the indicators, and you also have this monotonicity assumption where if you're missing at a particular time point, you stay missing afterwards, which sort of is meant to model dropout in studies. You also have a related block conditional model by Zhu, Little, and Kaltbleich in 2010. There's a permutation model, so-called permutation model by Jamie Robbins. There's the block parallel model that Karthika, Mohan, Yuda, Pearl, and Tian introduced. And there are many others. This is not a represented complete list by any means. And so what all of these models have in common, though, is that their restrictions, so they all have kind of independence restrictions that define them, they can be viewed as a factorization of the full data distribution with respect to a directed acyclic graph. And so just as a quick review, that's how this factorization works. So here is a directed acyclic graph. Here's a joint distribution on the left-hand side on 5 variables that could be represented as a product of factors. Each factor is a conditional that has a variable given its parents. And the point with these factorizations is that if the graph is relatively sparse, you need very few parameters to represent the observed data likelihood. So in the binary model, for example, you would need 31 parameters on the left-hand side if it was a saturated model. But using this factorization, we go down to many fewer. And in general, this is what the DAG factorization look like. It's just a product over every vertex, and you have a conditional of a vertex given its parent. Okay, so this is all very well known. And so we'll represent full law independence restrictions by this kind of factorization. And I just wanted to contrast the way missing data works from the way causal inference works. So in causal models are represented by lots of graphs. They're either called mutilated graphs or SWIG, single world intervention graphs, that represent different interventional or counterfactual situations. And so missing data are typically represented by a single graph with both observed and counterfactual variables in the same graph. And so these were first introduced to my knowledge by Karthika and Yuda. And so here is an example of such a graph on 2 variables, and this represents the 2 variable block conditional model. And so as you can see, there are these indicators and counterfactuals that are related by these blue arrows. And in addition, you have the proxy variables that have the indicator and the underlying variable as parents. And the gray edges are deterministic because, by definition, because the proxies are deterministically determined by the consistency property from those 2 variables. Okay. And so in these graphs, you have some restrictions on what you're allowed to do. So you're not allowed to have the indicator point into underlying counterfactuals, which is not so different from causal inference, actually. And also, each proxy only has 2 parents, which are the deterministic parents that it has. Okay, so otherwise it's mostly an unrestricted kind of DAG. Okay, and so you could use these graphs to represent many sort of missing data models in literature. So for example, a missing completely model has a restriction that the indicators are independent of everything. And here is the corresponding graph for that. This graph has the usual DAG factorization of the full data distribution, which looks like shown. And under this factorization, it's not so difficult to show that the distribution over the counterfactual variable is identified by this simple conditional. In other words, if you have data missing completely at random, it suffices to use observed cases for inference about functionals of the underlying target distribution, so which is well known, of course. So here we have monotone missing at random model. For simplicity, I just did a single time point. And here the restriction is you have some observed variables, and given those variables, missing variables are independent of their indicator. And this is the corresponding directed acyclic graph for this assumption, and the corresponding factorization, which is slightly more complicated than before because of this extra O. And under this model, if you were interested in the joint distribution of X1 and O, that's also identified by a slightly more complicated derivation shown here, which kind of looks like the G formula, if you've seen the G formula before. And of course, we also can have missing not at random models where events that lead to missingness depend on missing data themselves. So here is a very simple example where missingness status depends on the underlying variables that are being censored because of this green edge here. And this graph also has a factorization shown below. And it turned out that in this particular missing not at random model, the target distribution is not identified from the observed data. And that's because self-censoring, which is what the presence of this edge, kind of what I call it, it's sort of analogous to the presence of unobserved confounding in causal inference, and they both kind of lead to non-identification. And why is that? Well, there are lots of arguments you could make. Here's one simple one. We could just represent the full data distribution by a pattern mixture factorization, and we could represent the full data distribution by the just its factorization, and just notice that there are too many parameters in the full law compared to the observed law. So even in binary data, you have 3 parameters in the full law and 2 parameters in the observed law, so there is no way to recover everything. You just don't have enough dimension, basically. And you could also do explicit counterexamples of non-identification, where basically you can agree on the observed data, but disagree on the parameter. Okay, so a somewhat imprecise analogy with causal inference then is that the missing completely at random model is sort of like the ignorable model corresponding to randomized control trials, where you can just condition, because correlation is causation essentially. The monotone MAR model is sort of like the conditionally ignorable model, where you get identification by something like the G formula or the G computation algorithm in general. And MNAR models, it's not exactly clear what they are, so that's why I put a little question mark there. So it's sort of like, it seems like they correspond to causal models with hidden variables, but that's maybe not entirely right. The question is, are all missing not at random models not identified? Because I gave you a simple example where it's not. And as it happens, there are many, many, many identified missing not at random models. Many of them are represented by graphs. And so here I give 4 of them. It's not a representative list. There are more. So here's the block parallel model on 3 variables. There's a permutation model of Jamie Robbins on 3 variables. There's a block conditional model of Zhu, Little, and Kaufbleich. And lastly, there is a model called the no self-censoring model, or the item-wise conditional model. And this was introduced by myself and Stadidley and Ryder. Notice that this last model is not a DAG, and I'll come back to that. That's important. So missing data model of a DAG obeyed this kind of factorization, where you have these deterministic factors representing consistency. And because there were so many missing data models that correspond to a DAG, the arguments for identification is kind of scattered throughout the literature. And so the time has come sort of to do them all. And the question is, given any MNAR model, can we get the target law or the full law from the observed data distribution under the restrictions implied by this factorization? And so we'll talk about the second problem here first. And that's because the identification of the full law is actually very simple. Simple characterization once you see it. And to describe this, we'll first consider a model that is associated with a graph that isn't a DAG, which is the no self-censoring model, which was the last in the slide. And this model restrictions are that each indicator is independent of its corresponding variable given everything else. So all the other indicators and all the other variables observed or not. So this model is missing not at random because you have dependence on the counterfactual variables. It's also non-parametric saturated, so it doesn't impose any restrictions on the observed data. It does not correspond to a DAG, but it does correspond to a more general graph called the chain graph, which was introduced by Stefan Lauritsen, and yields this kind of hybrid factorization that looks a little bit like a DAG factorization, and each piece sort of looks like a conditional Markov random field. And so here for this 3-variable example, this is kind of what the factorization looks like, and the phi's are sort of potential functions, which are not necessarily normalized probabilities. Okay, and so this model is identified, it turns out. The full law is identified, and it follows from a factorization, a very clever factorization introduced by Chen. So the propensity score on all of the indicators can be written in this form. So on the denominator here is a normalizing constant, and on top are a bunch of Gibbs factors evaluated at indicators 1, and kind of a linking term, which is sort of a product of odds ratios, conditional odds ratios. And so you could think of this as kind of K parameters, a bunch of Gibbs factors and this kind of linking odds ratio parameter, and they're all variationally independent. And under the model assumptions, it turns out that each of these pieces are just functions of the observed data. So for the Gibbs factors, it's easy to see because you evaluate indicators at once, so counterfactuals become observed. For odds ratios, it's slightly harder to see, and so you could look at our paper to see what the argument is. It's a symmetry argument. And so what that means is that all the terms are functions of the observed data and form the chain graph factorization, and the full law is identified. So the propensity score is identified and the target distribution is identified. Okay, and so what is the relationship to DAG models? Well, any DAG model where it implies all the restrictions in the no self-censoring model is a submodel of it, and the submodel is identified. And if any DAG model is not a submodel of a no self-censoring model, it turns out it's not identified. And there is a very simple characterization that Rohit and Razi came up with, and here it is. All you have to do is draw yourself a missing data graph and look at whether it contains the following 2 structures: self-censoring edges, so those are bad, we know they're not identified because we had a proof earlier, or we have what are called a colluder. Colluder is a special collider where an indicator and its corresponding variable point to some indicator. So if you have such structures, then you have a problem, you're not identified. If you don't have those structures, then you imply the restrictions of the no self-censoring model. So we already saw that self-censoring is bad, so what about colluders? Well, it turns out with colluders, you could show, if you just restrict yourself to a 2-variable submodel that involves a colluder, you could run this argument that there is a part of the conditional distribution involving the colluder that you're not going to be able to identify, specifically when you condition on the indicator being 0. In other words, there are 2 parameters you could vary without changing the observed data distribution. And that means there's something in the full data that isn't identified. Okay, and so this is the end of the identification portion of the talk. So I'm going to pause here and see if there are any questions that from the audience that I could answer.
Thanks, Ilya. Yeah, so we have a question from Jonathan, whom I just unmuted. Jonathan, can you ask your question, please?
Yeah, so Ilya, you said earlier that you're not allowed arrows going from the observation indicators, the R's, back up to the X superscript 1s. And I just wondered why that wasn't allowed, and a situation where it seems like you'd need such an arrow is like dropout in a trial, where if they drop out and they're then missing an outcome measurement, the dropout often corresponds with changing treatments, and the changing treatments will then influence the subsequent unobserved outcomes. So it seems like there's sort of situations where I would like to have those, or I think I need those arrows there. And I guess I was wondering why they're not allowed.
So that's a good question. So actually, if you think about, so this is related to how we do things in causal inference. So in causal inference, this is actually also not allowed. And the reason it's perhaps not clear is because you don't usually draw causal diagrams this way. You don't put the underlying counterfactuals into the diagram. But if you do, you will see that you never, you never end up doing this. So what ends up happening is counterfactuals kind of exist and float there. So every person has a counterfactual Y1 and counterfactual Y0, and then they're coarsened by the treatment into the observed thing. And there are various complications that may correspond to something which you're looking for, which is something like interference, where somebody else's treatment influences your counterfactual. But I think, you know, I don't know if I can really do this live because I think I'm going to need the Blackboard, but I think my impression is these kinds of scenarios can be represented in a way that like disallow those edges anyways, but capture what you want essentially. Or you could just say, well, maybe you're right. Maybe you could expand these graphs to introduce these new edges, and then we'll need more theory basically to think about those kinds of models. Suffice it to say, the vast majority of sort of missing data models that people have looked at in the literature that do correspond to a graph correspond to this kind of graph where you have this restriction. So it's not so unreasonable because it captures a very wide class of models. Does that make sense?
Thank you.
Yeah.
All right, thanks, Jonathan, for your question. Dominic had a question. Dominic?
Yeah, just a quick one. So you said you can't have self-censoring edges, so from xi bracket 1 to ri. So what if you have indirect self-censoring? So you could have something from xi bracket 1 to rj, and then rj to ri back.
Yeah, that could be fine. So let me find some examples here. So yeah, so here's an example. Like in B, x31 points to R2, R2 points to x2, and x2 points back to R3. So there's a path from x3 to R3. It's just not direct. Okay. And this model is identified. So Jamie showed it back in '97, I guess. He didn't use graphs specifically, but it's not so hard to show.
Okay, interesting.
So yeah, it's specifically a direct edge that matters.
And like, could you even have almost deterministic relationship there? Because then it kind of gets closer and closer to real self-censoring. If you have, for example, an edge from x3 bracket 1 to R2, then from R2, let's say, to R3.
Right. So the R2 x2 edge is deterministic, because sort of definitionally so, because x2 is a deterministic function of its parents. I don't want to talk about determinism because once you assume determinism, it's no longer a non-parametric identification. You're now assuming other stuff. And it could be that if you assume more stuff, you get more identification than you did before. It's kind of like assuming linearity, right? If you're linear, maybe you are identified, right?
All right, great, thanks.
So I don't know, I guess.
Thanks. Yeah.
Thank you.
Okay, any other questions?
I think that's it from this end. Thanks, Ilya.
Okay, great. So I can keep going. Okay. All right. So this concludes the identification portion of the talk. So we should talk about inference. So we'll talk about parametric inference first. So if I have a DAG model that's a sub-model of no self-censoring, then what do we know? The target law and the propensity score are functionals of the observed data distribution. And we have a factorization with respect to a DAG. And so each factor is conditional in the full law because that's how DAG factorizations work. And it's some algebraic functional of the observed data distribution, meaning that I just like multiply things and add them and divide them. And those are simple functions, meaning that, well, good things happen with them. I can differentiate them. And importantly, the functional is not conditional in the observed law. It's only conditional in the full law. It's generally a much more complicated function of the observed data, but it is a function. And not only that, it's a smooth function because I can take derivatives. And so we have a smooth parameter map that's identified. And that means I can just maximize the observed data likelihood directly by my favorite optimization method. Importantly, I can always do this in missing data. Like this is just what the observed data likelihood looks like. I just marginalize things I don't see for a particular pattern. Importantly, though, if you don't establish identification first, then you could end up with the situation that you maximize likelihood, but you have a manifold of parameters that maximize it. And then it's not clear if you could, use it to guide policy or anything like that. But in our case, we're safe because we know we're identified. So we're going to get, with enough data, we're going to get a unique mode. And many special cases, it turns out, form exponential families. And so we can immediately run score-based model selection by using sort of BIC consistency arguments here. But I'm not going to talk about that because I don't have time. Okay, so that's parametric inference. And of course, assuming a full data likelihood is perhaps extravagant in applications. So instead, we could do semi-parametric inference, where we have nice, regular, asymptotically linear estimators that look like this formula here, where it's a sum of things where you have the influence function that you evaluate at every row, and there's this little bit leftover term that goes to 0 quickly. And so for us, the target parameter is going to be the mean of some fixed function of the underlying variables, which is what typically people do in missing data. And we'll discuss inference in the no self-censoring model because it's a supermodel of all the DAGs, basically. So we're going to get a consistent estimator this way. And we'll also have a subset of always observed covariance. Just to be general. And of course, because we have submodels that are DAGs, we know we can get more efficiency by projecting onto the tangent space of the submodels, but I'm not going to talk about that because it's complicated and I don't have time. Okay, so we're going to do the influence function in stages. We'll first derive an influence function with a partly known propensity score. And the way these missing data semi-parametric methods work, as I learned, is you first start with a full data influence function, assuming that you could see everything. And that in that case, it's simple because it's just the mean of something, and the mean has this influence function, which is just a difference. And then we kind of end up massaging this or applying kind of an operator to this full data influence function to get the observed data influence function. And so the simpler version of the problem we'll look at is we kind of know something about the propensity score. In particular, you know this log odds ratio for every variable that looks like this. It's just some functional form, you know. And in this case, the efficient IF has this form, and it sort of has the usual augmented inverse weighted form, where what you do is you look at your full data influence function, you do inverse weighting, that's the first term, and then you have an augmentation term that has to do with taking expectations of the full data influence function in a particular clever way. And importantly, it's not quite obvious, perhaps, from looking at this expression, but these are all functions. All the terms are functions of the observed data under the model assumptions and under the fact that we know this odds ratio. Okay, so but that's not quite the influence function in the model. It's just we assumed something. And if we don't know that odds ratio, then we have to add some extra terms to this. And then it turns out the influence function looks like this. We have this odds influence function and this extra adjustment term that looks like this on the bottom. And again, this is just observed data, although perhaps it's not quite obvious to see that. Okay, so that's what looks like. And this is efficient because we're non-parametric saturated. So there's only one influence function anyways. Okay. So often when you have augmented IPW, you have double robustness. This was a celebrated result back from the 90s. We also have double robustness, but it's partial. And so as usual, we can have this union model where we could specify correctly propensity score models for, or the this kind of outcome regression where outcome here is kind of the full data influence function. Provided though that the odds ratio is that this odds influence function relies on it specified correctly. And I think this is a general thing with missing not at random models. And I think it's related to the fact that there is no way to write down an inverse weighted estimator or a G formula type estimator in a way that uses completely complementary parts of the likelihood. You end up sharing something because of this missing not at random property. Whereas when you're missing at random, you know, like in monotone missing at random model, you can get full double robustness because you don't have to do that. And so, you know, we can only allow partial misspecification when we're being double robust here. We can specify things as long as the odds ratio remains correct, basically. Okay. So this is a brief slide to illustrate an important point about the imputation method. So if people, you know, lots of people have missing data, and the temptation is, if you have missing data, is you just deal with it and you just think of it as kind of data cleaning. And that's dangerous basically because, you know, what you can do is you can download a popular imputation package like MICE. This is a multiple imputation by chained equation. It's a very popular R package that people use. And you can kind of download it and run it and get some imputed data and then just kind of carry on with your life. And the point is that could be dangerous because mice relies on assumptions. If those assumptions are not met, you will be badly biased using mice. And so we were, so a talking point often is imputation methods seem to work well in practice. And the point is, you know, we just did this little simulation study to illustrate that that's not true. And if we're being mean to mice, we could certainly get it to produce a lot of bias for us. So here we just constructed a data generating process that happens to obey our model, where if I use our estimator, we have no bias basically, but if we use mice, we get a lot of bias, potentially policy significant amount of bias. And so, you know, just be careful. Okay. So that's our method versus imputation. If we decide to be adversarial, this is just some simple simulations pointing out that indeed we get partial double robustness, where if I specify the odds correctly, but misspecify one of the two propensity scores or sort of outcome regressions, then we remain more or less unbiased. Whereas if we specify both, we remain biased. And of course, we're unbiased if we're correct for both models. And finally, we did a very quick data application, this was an observational study of HIV positive pregnant mothers in Botswana. This was previously looked at by a number of other papers. And the interesting thing about the data set, it is pretty simple, but it has a lot of missingness and it's not monotonic, like 50–60% missingness perhaps. Here we binarized it for simplicity and just looked at the estimated joint distribution of three variables, which were important, which is whether antiretroviral medicine was continued during pregnancy, whether the mother had low CD4 count, which is a biomarker for HIV progression, and whether there was a preterm delivery, which was a worry for a pregnancy complication from heart, basically. And there was a lot of missing data on all of these variables in this data, and we just for purposes of illustration, estimated this joint distribution using three methods: just the complete case analysis, mice, and our method, and just pointed out that you get different answers. And of course, the practical guidance here, if you have missing data, you don't have strong feelings on what the missing data model should be. I think the thought is you should run a lot of them and compare, and possibly even do a sensitivity analysis before trying to base policy on what you find. Okay. So to conclude, there are many missing data models. Many of them factorize with respect to the DAG, to some DAG, despite the fact that many of them had kind of scattered arguments for their identification in the literature, there was no kind of unifying theory for all of it. And here we given a unifying theory for identifying the full data distribution by showing that all of these DAGs are submodels of a nice identified model called the no-self censoring model. And given that we're identified, we've described methods for parametric and semi-parametric inference. There are lots of extensions we could do. We could do efficient semi-parametric inference by projecting the influence function, no self-censoring model, onto the restrictions of the DAG submodels. These restrictions are sort of complicated, so we're not going to talk about this for now. We also have extensions to a characterization of identified models where you have missingness and hidden variables together. So I have some slides on that if we have time. And an identification of a marginal distribution where we only want to identify not the whole model, but just a part of it. And then things get a little hairy. And finally, it would be interesting to think about model selection methods in the presence of missing data, because there's this thought that because we have a nicely behaved, smooth model, we could probably show that in some special cases we get an exponential family, and then we could run BIC model selection. Okay, so here's the bibliography. Here are some papers that I took as an inspiration. Here are some papers that are relevant to what I've talked about that I'm a co-author on. And I would like to gratefully acknowledge my funding sources that helped me with this work. And that is the conclusion of my talk. Thank you very much.
Okay, great. Thank you very much for this nice talk, Ilya. So we will now switch over to the discussion. We will have Tian present a few slides, and then Ilya can respond. And then in the end, we might take some more questions from the audience. So if you have some more questions, please submit them via Q&A. Okay, so now I'm switching over to Chen.
Okay, let me share the screen. Okay, can you see the screen now?
Yes.
Okay. Okay, first, thanks, Ilya, for a great talk, and thank the organizer for inviting me to discuss this. As Ilya mentioned, missing data are ubiquitous in data-driven fields. So in principle, to analyze data with missing values, we need to understand the mechanisms that lead to the missing data. In particular, whether the fact that variables are missing is related to the underlying values of the variables. To model this missing data mechanism, we introduce missingness indicator variables. For each variable xi that could be missing, could have missing values, introduce an indicator variable r. Now, for the audience who are not familiar with the identification problem, I will show a simple example to demonstrate the issue here. Consider a simple problem. We have a single binary random variable x. And we have some observational data with missing values. So those question marks means missing values. Our goal is to estimate the distribution of x from the missing data. Well, it turns out whether this distribution of x is estimable or not actually depends on the reasons for missingness. For example, if the missingness mechanism is missing completely at random, whether this value is missing or not is independent of its underlying value, then we can estimate the distribution by simply ignore all the missing values. For example, here we have 5 observations. Out of 2 of them is 1, then we can use this to estimate. On the other hand, if the missing is missing not at random model, whether the value is missing or not depends on the true value of x. For example, in a salary survey, people with low income are less likely to reveal their income. Under this model, even if you collect the infinite amount of data, this marginal distribution of x is still not estimable if we do not know exactly how the probability of Rx given x, if we do not know the value. Why is this the case? Because in general, you can imagine 2 completely different missing data mechanisms. One mechanism, x is missing if and only if its true value is 1. Under this model, all the missing values are actually 1. Then you can get an estimation. On the other hand, if the missingness mechanism is that x is missing only if x value is 0, then all the missing entries should be 0. You will get a different estimate. So that's why we say if this is our model, then the px is not identifiable. Here we are going to assume we do not know exactly the distribution of Rx given x. So that's the identifiability problem. To model in general, to model the missing not at random settings, we may use graphic models, particularly a DAG model. Missing data model could be decomposed into a data generation model and missingness mechanism. It's common to model the data generation model using a DAG model. They are known as causal DAGs or Bayesian networks. Here, the idea is we are going to also model in the DAG the mechanisms, the missingness mechanisms, how those R variables depends on the X variables. So this kind of graph, they are known as the M graphs. So, okay, I think we got a question back then why we do not allow the error from the R variables to the X variables. Because the assumption here is the data generation model is independent of the missingness mechanism. So we have a completely independent data generation model, modeled by a DAG. Under this model, for example, one is a missing mechanism, missing at random. If none of the variables with missing values are parents of the R variables. In other words, whether the R variables are not directly influenced by any variables which have missing values, then the model is known as missing at random. If the data is missing at random, it's known that all the distributions are identifiable. So in the identifiability problem, we are concerned with the problem that if we are given a M graph, so we know the graph, which describes the qualitative relationships among those variables, and we have observational data, which could have possible missing values. We ask a particular probabilistic or causal query. For example, if you're interested in this conditional probability or if you're interested in this causal quantity, we ask, is it possible to estimate them from observational data? And in particular, we are going to assume we have infinite amount of observational data. So we assume we are given observed probabilities. Then the formal definition of identifiability problem is given the graph structure and given observed probability distributions is a particular query completely decided by the observed distributions. And in particular, in this definition of identifiability, we actually assume that we have observed all the missingness patterns. So for all the possible ways of data could be missing, so for any subset of S, we observe the distribution. So including the complete data distribution, you observe all the variables, including all of the S are missing. So one here is a question or maybe ask comments from Ilya. Is this assumption actually realistic or common in practice? That is, can we actually assume all the missingness patterns are observed? We know in some applications, for example, truncation by death, the problem actually forbids certain combinations of events from occurring. Can we solve the identifiability problem, for example, only given some subset of this observed distribution instead of all of them? So today, Ilya present a complete condition, a necessary and sufficient condition for identify the full joint distribution. So that's a great result, the first completeness result in on this topic. In practice, we often are interested in the data generation model. So unfortunately, even if this joint model of R and X is unidentified, it's still possible that the observed data model may be identified. So at this point, we still do not have a complete condition for this. We have some sufficient condition for this problem. And in practice, perhaps a more interesting problem is for any specific target query. We are not really interested in the complete data model. We might be interested in some particular probabilistic query. And question is, can some particular probabilistic query be identified, even if the full joint distribution is not identified? This question, again, is open. We do not have complete conditions at this point. And also, we might ask interested in causal queries. Even if those distributions are not identified, some target causal queries may be identified. That's, again, an open question. At this point, we don't have if and only if conditions for that. So that's the identification problem. The estimation problem, we are concerned with assume your target query is identified. So it's typically will be expressed in some very complex expressions. In the estimation problem, we don't assume we have those distributions. Instead, we have finite number of examples. We would like to estimate this quantity from finite examples. So that's the estimation problem. Today, Ilya present IPW estimator assuming there's no self-censoring models. So I do have some questions for Ilya. So does the result you have need additional assumptions? For example, do you need to assume the model is non-parametric saturated? And also, is your results applicable to any identified query or just the joint distribution? And also, we know that in general, the probabilistic inference problem in Bayesian networks, they are NP hard problem. Even approximate inference is NP hard. Can you comment on the time complexity of your algorithm? How did you overcome the NP complexity issue? And also, a naive idea for doing probabilistic inference could be estimate the condition, those factors, each variable given its parents. If I can estimate those, identify those, then in principle, I could use those standard Bayesian network inference algorithms. So I wonder, is this a good idea or a bad idea? Finally, for the missing at random model, typically in machine learning, we use EM algorithm. Can you give some comments about the EM algorithm compared with your algorithm? So in missing at random model, should we use EM algorithm or should we consider using your algorithm? Okay, that's it.
Okay, great. Thanks, Jin, for your discussion. Ilya, do you want to respond?
Yeah. Would you mind keeping Jin's slides up? I tried to take notes on the questions, but I might miss something.
Sure, sure.
So thank you, Jen. This was a wonderful, wonderful discussion, and you have a lot of good questions. And in fact, I'm glad you asked the first question about patterns. I think somebody else, I think Thomas asked this question too, and I think maybe I misunderstood it. In missing data, typically you assume that some patterns need to be there, which is sort of a point I glossed over in my talk. So the typical assumption is you need complete cases. So in other words, the pattern of all ones has to be there. And this is sort of related to no overlap. Otherwise, you can't make progress if you don't even have complete cases. But what other patterns you need sort of depends on the model. it turns out that the only patterns that you need for the no self-censoring model are the complete cases and cases where you have all of ones and a single zero. So in other words, you need all variables be there and all but one variables to be there for all variables. As long as you have those patterns, you're fine, basically. It's true that in missing data in practice, you will have, if you want to think about it in terms of indicators, you will have 2 to the k indicators, which is a big number. And so you'll have a lot of missing patterns, and that's a problem. And I think one of the interesting open questions for this work that I haven't talked about that is important is how do you extend inferences in this model to cases where you have missing patterns, including patterns that the model actually needs, which is the all but one. So the complete cases we're going to have because all missing data needs it. But what happens if you have a missing pattern where like there is some variable where the zero for that variable in all ones is a missing pattern? Like, what do you do there? Technically, this stuff is going to, that I presented, is going to blow up then. But it's possible to, maybe make more assumptions to get around this. So that's patterns. And in general, there's a lot of interesting work to be done thinking about patterns. Like the monotonicity, monotone missing data, if you think about it, is a pattern restriction, right? You just rule out non-monotone patterns. And I think it's a very fruitful thing to think about is how does identification change when you only allow certain patterns and not others? Okay, so that's the first question. Non-parametric saturation and other queries. So non-parametric saturation is just a property so much rather than an assumption. It's just saying that I have this model. If I look at the full data distribution, it has restrictions there because factorizes ag. But of course, the observed data is not the same as the full data because you end up summing things out. And then if you do that, sometimes you will have restrictions in the observed kind of margin, and sometimes you won't. And so this is analogous to hidden variable DAGs, where the underlying DAG could have restrictions, but once you do the latent projection, the restrictions disappear. So for example, in an instrumental variable model, there are restrictions in the full data, but once I sum out the unobserved confounder, I have inequalities, the IV inequalities, but I don't have any independence restrictions in the observed data anymore. So non-parametric saturation just means that you don't have any restrictions like that. And so this no self-censoring model happens to have the property that there are no restrictions. So any observed data distribution is compatible with this model. And this is actually a good property to have in missing data, because if it's not true, and you're going to apply a missing data model that imposes restrictions, then if you want to be a careful statistician, you should actually check that your data supports your restrictions. Otherwise, the model is probably not appropriate. Okay, so that's that. Other queries. So typically in missing data, like the starting point for doing semi-parametrics is you assume some full data functional, and then you derive the observed data version of it. So you were asking questions about the conditional distributions maybe, or causal effects. And this machinery works for that. Meaning that as long as I'm in a no self-censoring model, the full data distribution is identified, so all functions of it are also identified. And for conditional distributions and causal effects in the full data, there are known influence functions. So for example, if in the full data I can adjust for confounding, so I can use the backdoor criterion, then there is an influence function called the augmented IPW based influence function for that functional. And then I could project that influence function onto the observed data using this kind of inverse weighting thing that I've described. So all of that just immediately follows. The other question you asked is what happens about other queries, and of course that, as you say, this is what if the full data isn't identified but the other queries are, and of course, as you know, there are no complete conditions yet. So we're working on it, but we have some slides on this, but it's really hard basically. Time complexity is it's like if I'm doing parametric inference, that is using Bayes nets essentially. Because if in my maximum likelihood slide, I just said, well, I have a bunch of observed data. I have a bunch of full data kind of factors, and these factors are all functions of the observed data. So in principle, I could just evaluate each row and do some extra sums to account for missing data. And that's just basically Bayesian network inference. And of course, it's going to be intractable unless it so happens that the Bayesian network is sparse, in which case doing those sums could be done efficiently using variable elimination. And we could think about that. So essentially, standard, doing maximum likelihood on my slide is using standard Bayesian network inference algorithms with the additional twist that I have to do the missing data summation for every pattern, essentially. As far as computational complexity is intractable in general, for semi-parametric stuff, it's solving estimating equations. So it's this complicated optimization problem. I don't know if it has a fixed running time. It's like the usual optimization stuff. You try to run it to a local maximum and hope for the best. And there are lots of tricks for doing that. I don't know if people have done a lot of closed form analyses of how long that takes in practice. These influence functions are not so easy actually to optimize. Comparing AIPW with EM. So EM is a likelihood method. So I think it's sort of comparing apples to oranges. So semi-parametric methods don't assume a parametric likelihood, really. The way people often do them in practice is maybe they use, there are pieces you need to model in the influence function. So you have the propensity scores and you have the outcome regressions, and you could use parametric strategies for those, or you could use machine learning, for example, to learn those curves, in which case you're comparing something that uses machine learning to something that uses a parametric likelihood. And I'm not sure how meaningful that comparison is, because basically you assume a likelihood to do EM, but what if your likelihood is wrong? And then you will just get garbage. And the fact that you ran efficiently doesn't actually help at all. So our estimator, the AIPW estimator, doesn't apply to MAR. It applies to the no self-censoring model. For MAR, there are existing influence functions that are basically look like augmented IPW. So for monotone MAR, they look like, they've been worked out a long time ago by Jamie and Andrea and company. Yeah. And I think as far as different missing data models, I wouldn't necessarily like compare them against each other. It's more like I would run them all, because if I have an applied analysis like this Botswana study and I don't know which missing data model to use, then the careful statistician thing to do is to just run many missing data models that get different answers and just say, under these various assumptions, this is the full data distribution that I got, take this, make decisions as you will, basically. Yeah, and as should AIPW be used in MAR models. Yeah, I think semi-parametric is good to use. It's a great way to get around not having to have a full data likelihood, but still have parametric properties like asymptotic normality and root end consistency and things like that. It's just kind of the whole point of these methods. I think that's all the questions, I hope, right?
Yes, and I think we also should slowly wrap up now. Sorry.
Okay.
All right. First, thank you very much, Ilya, Chen, Tian, and Rohit for volunteering today. It was a fantastic talk, discussion, and also thank you very much for answering questions in the chat. Now switching over to next week. Yeah, so next week we're going to have Susan Murphy from Harvard give a discussion. We're very much looking forward to that. Thank you all for joining today. Please stay safe and see you next time. Thank you.